Sorry. Okay. Sorry, it's 10:30. Okay, I was just trying to figure out the technology. Sorry, everyone. So there's like someone that can't, there's at least one person that can't has a time conflict. And so hopefully the audio works. So I need to record everything. And I thought this was the easiest way to do it. And then I didn't think through the fact that whatever, there's too many screens. Hopefully this is gonna be big enough. I can't figure out how to make, like, I don't need all this garbage, right? Like, anyone know how to make it just the screen share that I'm crazy? Am I crazy? Minimize like this? Yeah. I just don't know. But yeah, I just don't know how. Oh, okay, do that. Give it a little more. Come on. You can do it. And like all this garbage. We don't need 1,000 toolbars. Windows. What is going on? So, am I crazy? Anyone else know how Windows works? No? Well, I am sharing my screen.
It just won't. I mean, I think for me,
Sorry, what? Say that again?
like press the share button. No, but it just won't.
I am sharing a screen over here. Right? Yeah. Okay. Am I crazy? Okay. Did I miss something? Okay. Yeah, I think it's just because I have this. Maybe I'll see if I can get a better like, sorry, shit. I'll see if I can get a better setup to have it view from here as opposed to like just get rid of these stupid bars. I just don't want all the bars. Am I right? Pop out, maybe pop out. Ooh, that's better. Okay, that's less bars. Okay, that's better. Yeah, a little better. Okay, sorry. Okay, and how's the lighting? Good. Okay, hi. I think I've met all of you, hopefully, but I'm Kim, if not. So I'll be the instructor for Math 730 for algebra. So I sent out a little email last night. Did hopefully people get the email? I put it as a group because it's a mess. So that's so I sent a link to the course site, and I can share it, but that will take more technology moving around, which nobody wants. So hopefully you can access, everything's just going to be on my like personal site. Like I said, because there's like a few people sitting in and like a bunch of different things. So all the resources should be on my personal site, including like slides and stuff like that. And the syllabus. I will have Canvas. It's not like up to go, but I mostly will just use it to record grades because yeah, it's just too much duplication. Good. Okay. So right now, we meet Monday, Wednesday, Friday at this time, and I'm planning to do office hours on Monday, Wednesday at 3:30 to like 4:20ish, and then also on Friday at before class. My thought was that hopefully my plan was to hopefully do the Wednesday office hour like an option. So where we could work on problems together, whether they're homework problems or, like recommended problems. So that was my thought, and I would have that in the QLC. That's what I have set aside. If that's something you want to attend but can't, I can try to be flexible with the hours. I just try to make it not overlap with any of the other grad classes and stuff like that, but I can try to move stuff around. So again, not a mandatory part of the class, but just what I thought would be helpful. So I'm happy to have feedback on those times though. and move things. Okay, so overview from like what was on the syllabus and stuff. Participation I have on there. I think what I'll try to do is steal something from Virginia, where at the beginning of each class, I might call on someone and have you just summarize like 2 sentences what we did last time. We defined a group, we proved this thing, that's all you got to do. But just to make sure, just to kind of encourage you, look through your notes from last time, read what's going on, stay engaged. That was my main thought for the participation, nothing crazy, just, you know, showing up, answering questions, asking questions, staying engaged. Homework is only worth 20%. For a lot of reasons, but it's going to be, I'm going to try to do weekly assignments due on Fridays. The first one's posted, it's not due this Friday, it's due the next Friday. The way I put it is that like there's a bunch of problems listed, and then I bolded the ones that I want you to turn in and I will grade from. I recommend doing all of them, but like there's more than, I know there's going to be too many most of the time. And so, you know, sometimes that's not going to be feasible and I totally get it. But I think there's like 8 due next Friday or something like that. Those are the ones I'll grade from the homework from. And then quizzes I'll have on Mondays. At the end of class, they're going to be really short. They're just going to be based off the definitions and major results from the previous week. So just, I would recommend like making some flashcards or some sort of study notes just to kind of keep the main things. There's a lot of definitions and terms that throw out in this class, and so I thought that was a good way to stay on top of things. So they should be very quick, you know, maybe some examples or things like that, very straightforward. If you took 511 for me, something of that flavor. But if not, we'll see. Cool. And then I'll probably, I didn't put this on the syllabus, but I'll probably end up dropping like 1 or 2 because I know that you guys are probably not, you know, it's fine to miss things. And then let's see. Oh, there's a midterm. Right now I have it scheduled for Friday, October 16th. I tried to get information from the other qual people, or the other qual class people to make sure there wasn't an overlap, and so far there's nothing. And then the final exam is on Wednesday, December 16th. That's just like the university set time. Cool. Questions about format or like grading structure or anything like that? Pretty straightforward, hopefully. Okay. So for, I think the most important part, I was looking actually just this morning about when I took this class an unmentionable amount of time ago. And I remember being like, oh my God, that class was so much work. And then I looked and I had 30 problems due the first 2 weeks. And it took me 34 pages to write them up, but I learned so much. And so I think, and this was, what goes without saying, was before AI, and it was before you could Google a problem and be like Dummit Foote number 7, and you would never find Dummit Foote number 7, right? So I cannot stress enough how much I know AI is a resource out there. I know you can find solutions to a lot of these problems outside. But I'm going to try to grade things in a way that you will not be penalized or be minimally penalized for getting things wrong. And I really want you to try the problems on your own. That is like the only thing that you can get from these classes is like trying the problems, learning to think through things critically. I tried to not assign so much that is due that you cannot do that for this very reason. So I really recommend to like try each of the problems, like right after we cover that section, maybe look it over, think about it, you know, write it down, think about it, go back, maybe take a stab at it again the next day. Just take your time with the assignments. And when you get stuck on something, you know, ask your classmates. I think a lot of you know each other and hopefully we'll know each other better. And then come to office hours, those kinds of things. Like I would rather you did all those things, and I will try my best to make it a way that you will not be penalized by your grade if you do that, because I think that is the way to learn. Seeing a solution will only get you so far. And I think that that is kind of one of those problems that especially if you're taking a qual later on or you need to use this information, like that's really going to hurt you in the long run. And I cannot stress that enough. Okay. So it's not just me being afraid of technology, which I am, but it's also for a real reason. Okay. So yeah, what I think I'll end up doing for the homework to make that not as difficult is I'll probably end up giving you a grade for like the homeworks and the exams based off of like, if this were a qual question or whatever, like this is how I would grade it. So you can be clear about what the expectations are as far as like what I want you to write. But I also will be very lenient for like your course grade point wise. So it might be like this was a C if you answered this on a qual, but like you got an A because you got the major points and whatever. And so if that makes sense, I'll try to make it clear what I'm going through, but I just want you guys to know I will minimally be penalized by like missing the content as long as you're trying to get it. Okay. Great. And I mentioned the recitation thing. You can let me know about that. And then just general things for succeeding in the graduate class. Like I said, I recommend like looking at the problems after we cover that the corresponding section. Read your class notes after and the text before class if you can. And then if there's anything that's like left as an exercise from the class, like any major theorems that we didn't get a chance to fill in, I would try to like, prove those things in between the classes. Make flashcards of key terms and theorems as we're going along. I think I linked on the website some resources. There's a really good like online flashcard thing where you can it will quiz you and stuff like that. So, I mean, yeah, and I should say AI in that sense can be very good, like having it come up with problems for you, helping you study, like that stuff's great. I'm totally fine with that. But like solving the problems is where it's gonna get fishy. And then, yeah, try your exercises on your own first, but you're welcome to work with others and talk to each other. I encourage that highly. Cool. So I think that's the overview. Any questions from the course part overview stuff? Okay, great. I am very excited. So I'm very excited for this class, and I hope it's a lot of fun. And part of the reason I'm excited for this class is like the history of the subject is so really of algebra is really interesting. And so we're going to really start off the first part of this semester with the notion of a group. And we're going to work through definitions and examples and all these implications. And what makes a definition of a group so interesting is that it encompasses so many different phenomena. But what it's trying to get at is a structural commonality, and you can prove so many different things just from like the structure of objects like this. And so the way that this theory was developed was like basically from a lot of examples. And what a lot of these really cool bigger theories come from is you build up a bunch of different examples and you get some tools based on what you think are very specific things. And then those tools can eventually generalize and you can prove and then you can use them in other unexpected ways. So one example of where some of these tools and the notion of a group came from is from number theory. I think one of the nice canonical examples is in Euler's theorem. So Euler proved this in like I think it was 1761. But he used ideas of Lagrange that and the theory that would later develop into Lagrange theory and Lagrange's theorems. And now you can see Euler's theorem as a specific case of Lagrange's theorem. So Lagrange's. So another example that's more related to geometry, but kind of a hybrid between geometry and number theory is the case of elliptic curves. So one question would be like, how many rational points are on a particular elliptic curve? And so an elliptic curve is something like, oops. A rational a function and so an elliptic curve is a function. Well, it's not exactly a function. It's an equation given by, instead of y equals some cubic, it's y equals, or y squared equals some cubic. Something maybe of this form. And so we might want to know how many rational points would serve as a solution, like rational points x, y would serve as a solution to this elliptic curve. again, I think it was Euler that used elliptic integrals to solve these problems, and then used like a geometric operation to generate more solutions from previous ones. And so the structure of these solutions has like a geometric structure that's modeled by a group. And this is something that kind of developed as its own area and really was like one of the foundational examples that makes group theory. And then the last one that is maybe the most commonly known is solving algebraic equations. And so this is really the motivation, especially for the second part of this course, is finding solutions to the general quintic. So by the 1800s, so by 1824, we had general solutions to quadratic, cubic, and quintic equations, or sorry, quartic, I'm sorry, quartic equations. So we all know the general solution to the quadratic equation, right? It's the quadratic formula. We all memorize that. And in some places, you maybe, if you maybe went to school in a different country that has a better education system than ours, maybe you even learned the general formula for the solution to the quartic, or how to find a the cubic, or even in the quartic. So we can write down a nice closed form solution for solving any quartic equation. And then the natural question was, well, can we do this for the quintic? And it turns out the answer is no. And the reason why, the proof why we cannot find a general solution for the quintic stemmed out of Galois theory. Okay, so we cannot do this. And we can't find one for the quintic, not because we're lazy and AI will get it for us, but because it's impossible. Cool. And so Galois theory we're going to see next semester, not in this part of the course, but that was really kind of where things stem from. Okay. And so the reason these abstract definitions are made is because it's useful to isolate specific characteristics and consider the structure when imposed on an object having those characteristics, right? So that's what groups are really going to do, is they're going to unify these different phenomena and allow us to just identify the characteristics that are actually important in the proofs. Okay? Questions? Okay, so let's start off with basic definitions. So what is the basic definition of a group? Well, a group is going to be an ordered pair. And sometimes we'll just refer to it by the set G. But we're going to think of it as an ordered pair where G here is a set and star is some sort of binary operation that satisfies a few axioms, right? So we have a binary operation. And what is a binary operation? Well, it's some sort of function from the cross product, so G cross G, from like an ordered pair to G. Right? So we're just thinking of this binary operation is going to take two elements of G and do something with them and pop out another element of G. So examples of a binary operation: addition is a binary operation, on the integers, right? I can take two integers, I add them together, I get out one integer. Multiplication is a binary operation on, the integers or the real numbers or whatever you like, all those things, right? So we take a binary operation and we need this binary operation to satisfy three different characteristics. We need that this operation is associative. And so what does associative mean?
We can change the order of the brackets.
Yeah, perfect. We can bracket them in different ways and we get the same thing. Very good. Parentheses don't matter, basically, right? So A star, B star, C for all A, B, and C and G. Okay. And then we also have that there is a identity element in G. So there exists an element E in G called an identity. And so what does that identity do? What it means, for E to be an identity, it means that if I take any other element of G, A star E, is the same thing as E star A, and we get the same thing out. It just gives me my same thing out, right? Identity with respect to that operation. And then the last thing we need is that we need every element in my set to have a inverse under this binary operation. So for all A and G, A has an inverse in G, also contained in the set, right? So what does it mean to be an inverse? It means that when I take that binary operation between A and A inverse, it gives me that identity element. And notice that both inverses and the identity element commute well, right? That's not necessarily going to be the case for every element of the group. So for an arbitrary group G, we may not have that this binary operation is always commutative. That only happens when we call this group, or that happens in some particular cases, and we call that group abelian. So this group is abelian, or sometimes called commutative, you know, what you would normally want to think of as commutative if A star B is equal to B star A for all of the A and B and G. So for every single element. Not just a random pair you can find, but all of the elements in G. Okay. Great. Questions? Okay, so we usually call this abelian, but I know in other contexts, this is like a commutative, we'd call this commutative. So a couple things to note is one, we say G is a group under star when you look at this ordered, when you're really calling this ordered pair a group. When I say this ordered pair is a group, kind of the more natural way to say it is that G is a group under star. And so in that sense, it's also very important to talk about, because each group is really an ordered pair, it's really important to specify both the set you're talking about and the binary operation, unless it's like very obvious from context. But we already know integers, we have many different binary operations floating around, like multiplication and addition, right? And so you can have some things be a group under one operation and some things not be a group under under a different operation. Cool. And I'll also say we say a group is finite if the set G is finite. We say a group is finite if the set G is finite. So if I'm talking about a finite group, what I really mean is the set what we're talking about there is finite. Okay, cool. Questions? Straightforward. Okay, so let's look at some examples. We already kind of touched on a few things that might play a role here. So examples. So we talked about certain binary operations. So the integers, the rational numbers, the real numbers, and even the complex numbers are groups under addition. And in fact, they're all abelian groups, right? Because addition is commutative for each of these sets. And so whenever I'm thinking about what a group is, it's nice to think about whether that operation is actually commutative. In this case, it is. Those are abelian groups. And also, what is the identity and what do inverses look like, right? And so what is the identity element in each of these sets? Or in each of these groups, I should say. 0. Very good. So 0 is the identity. And if I'm thinking about what the inverse is then for any element, it's really just like negative A, right? So what's the inverse of 2? It's negative 2. Anything I'm saying or writing isn't clear, let me know. Okay, other examples. Okay, so we already said we have other binary operations. We don't have just addition, right? We have multiplication floating around, but I should be a little bit careful about multiplication when I'm thinking about these sets, right? I have to be, if I look at the integers under multiplication, is that a group? Being tricky, sorry, but you know the answer. Okay, what do I have to worry about? I do have to worry about inverses. Very good. What about the rational numbers then? Being tricky. Not quite. What do I have to worry about? 0. I have to be worried about 0. Okay, good. So for the integers, you're exactly right. I don't have multiplicative inverses, right? I don't have 1 over, well, I don't have a half in the integers. But if I now look at the rational numbers, Q, and I remove, as long as I remove 0, or if I look at the real numbers and I remove 0, or the complex numbers and I remove 0, these are all abelian groups under multiplication, right? And here, my identity element is no longer 0 because it's not even in the group. What's my identity? 1, right? And inverses look like just reciprocals, right? Great. Okay, cool. So basic examples that we're pretty familiar with, hopefully. Any questions about them? Okay. Another example that comes up that you've maybe hopefully seen before, is vector spaces. So vector spaces under vector space addition. And again, another nice example of now all the groups that we've been talking about. Well, I guess vector spaces can be finite, but most of these groups that we're talking about in 1 and 2 here, the groups we've talked about 1 or 2 are all examples of infinite groups, right? Because their sets are infinite sets. But a finite group that we might consider is Z mod NZ, for n a positive integer. And so this thing is a group under addition of residue classes. Right, so what is Z mod NZ? It's the set of all equivalents or residue classes mod n. So everything equivalent to 1 mod n, 2 mod n, 0 mod n, right? And so on. And I can add those equivalence classes, that's fine, or those residue classes, that's the operation there, and that thing forms a group, right? Because I do have additive inverses under residue classes. So if this is not an example that you're super familiar with, I would really recommend, there's a nice, very quick precursor section 0.3 of Dummit and Foote. And they build things up in the rest of section of this preliminary section 0, just to make sure you're comfortable with these residue classes. Okay, and so these are groups under addition, right? We just, again, the equivalence class mod. If I want to find the identity element, that's just 0, right? The identity element is the 0 equivalence class, or the n equivalence class in this case. So the identity element is the 0 equivalence class, or that's the same thing as the n equivalence class. And I can also find for any inverse, I'm just going to have negative the equivalence class, right? Or whatever thing adds to 0, Cool. Great. I could also multiply sometimes in residue classes, right? But I have to worry now if I'm looking at just Z mod NZ, and I want to think about this thing being a group. Well, okay, associativity seems fine if I multiply in residue classes. Sure, I still have an identity. I still have the one equivalence class. That seems fine. But now I have to worry about inverses if I'm looking at all of Z mod NZ. If I'm looking at the equivalence class mod N, so mod 4, so if I think of Z mod 4Z, right, this looks like the set of 0, 1, 2, and 3. And I can ask myself, does everything here have a multiplicative inverse? No. What do I worry about? 2, right? So 2 does not have a multiplicative inverse. So you can test it out and prove it to yourself. And in fact, we know for any Z mod NZ, which of the elements are going to have a multiplicative inverse.
Ones where the greatest common denominator is combined.
Divisor, greatest common divisor.
Divisor.
Exactly right. Yeah. Okay, so A is has an inverse, right? And I'll say A in here has an inverse if and only if GCD of A and N is equal to 1, right? The greatest, if they're co-prime, or if the greatest common divisor is 1. And so that's what we call this group of units that we denote with the times here. This is the equivalence classes. This is the stuff that's all relatively prime to N. So notice 0 is not going to be in this set, so we don't have to worry about 0 not having a multiplicative inverse. But this thing is a group under, and it's abelian also, under multiplication of residue classes. Cool. Great. Great. And so this is an example where whenever we put this times here, I'm always talking about the group of units. And sometimes I'll do that here. If I say Q, if you see Q times or Q cross, that's really just removing 0. So it's like all the stuff with multiplicative inverses is usually what you mean. And so this is always referring to the group under multiplication. And this, but without the times, that's always referring to the group under addition. Okay, so sometimes we won't mention the operations there. So, but in your book or what have you, so this is always talking about something under times because under addition, we don't have the inverse there. And then this is always under plus. It's just like implied when I use those, when I just refer to those sets. Okay. And then a last example is kind of a type of example. So another thing we can do to make a group is I can take the direct product of two other groups. So for example, if I take, say I have A star and B dot are two groups. So I have a set A and it becomes a group under whatever the star operation is. And I have a set B and it becomes a group under whatever the dot operation is. Then A cross B, which is the set of all ordered pairs. So that Cartesian product is a group under the operation move this down a little bit. Under the operation. So when I take two elements, let's see, I take A1 B1 and I perform like diamond A2, B2, this operation, whatever I'm calling it, diamond. I'm not doing a good job of writing here. There we go. Looks like A1, well, the operation on A stuff was star. So I'm going to star both of these A's, and the operation on B was dot, so I'm going to dot both of the B's. Cool. So this is called the direct product. There are other ways that we can product two groups and get another group that we'll talk about later, like semi-direct products and other things, but this is kind of a nice natural way to do it. And so specifically, if I take R cross R is a group under where both operations are, where both like star and times are multiplication, or sorry, addition. Cool. So if I took addition in both components, it's a boring example, but you can make more creative examples, but that's one. Okay, cool. Question? Okay. Cool. In fact, you could take any two of the other examples we had. Okay, great. So something that we'll see when we're talking about kind of examples of groups. Can everyone read this okay in the back and everything? Is this big enough? Okay, cool. It's a small projector. You might sometimes be asked to list things as a group table. And so a group table looks like, so if we're looking at Z8 cross, let's see here, go. Do that. So if I'm looking at Z8 cross, so what is a group table? It's basically a matrix. It's a is a n by n matrix. If your group has n elements in it, it's an n by n group matrix whose ij entry is the group element gi gj. Okay, and so if I'm looking at this example of z mod 8z under multiplication, z mod 8z cross, right? So as a set, let's see, this thing is the units in z mod 8z. So, or the things with multiplicative inverses. And so we throw out 0, but of course we have 1 because that's our multiplicative identity. We don't have 2 because that's not relatively prime to 8. We have 3, not 4 because not relatively prime, 5, and 7. Very good. So we just have these 4 elements. And so my table should be a 4 by 4 table. 3, 5, 7. 1, 3, 5, 7. And I'm just going to fill it in by like looking at what all the multiplication of the things are, right? So this first row and first column are really boring because this is just going to be 1 times each of the other equivalence classes. So 1, 3, 5, 7. And the first column is also boring, right? Because it's 1 times these equivalence classes. Okay, now I take 3 times 3, and that's 9. But mod 8, that's really 1, I think. Right? Stop me if I'm wrong. Multiplying is a hard thing in front of people. Okay, and then I take 3 times 5, right? And that's 15. And mod 8, that's 7, right? And then 3 times 7, that's 21, which I think should be 5. Cool. And I think we can do the rest. 3 times 5 we said was 7. 5 times 5 is 25, so that should be 1 since 24 is a multiple of 8. And then 5 times 7 we said was 3. I think should be 3 because that's 35. Yeah. And then 7 times 3, I think we should be able to do the rest of this. So it should be 5, 3, and 1. But you can check me to make sure I'm not crazy. Okay. And so what's nice about the multiplication table here is we can see what the inverse of every single element is. 3 is its own inverse. And then, of course, 5 and 7 are each other's inverses. No, wait, 5 is everybody's its own inverse. Sorry about that. I misspoke. Everybody is its own inverse. In here. Okay, great. Cool. Questions? Okay, awesome. Moving on. Okay, so great. So there's a couple of nice little propositions in this section. So one of them is that if we have a group, so basic things we can already say about groups. What we have is 3 axioms. We have a bunch of examples of things that fit there, but my axioms are associativity, identity exists, and every element has an inverse. Well, the first thing we can say is that the identity is unique. Meaning there's just one of them, right? If I think I have 2, really those 2 things are equal. And so same thing with inverses. For each element A inverse is also unique. No element has 2 different inverses. Okay, maybe other useful property. If I take any 2 elements in my group, A and B, and I take that binary operation of them, I get an element in the group. Now, of course, that thing should have an inverse, right? And what does the inverse look like? Well, it looks like take the inverse of B and compose it or whatever, take the binary operation with A inverse. Okay, so meaning like this order, I guess. That's where the grouping is happening. That's not clear. And then the last one is maybe slightly more intuitive, or you probably very quickly extrapolated, which is that we have the associative operation on 3 elements, right? We said A star B star C. Doesn't matter what order you put the parentheses, but you can really quickly extrapolate that to any n, right? And for an arbitrary expression length, those things can be bracketed in kind of any way, and it's very fine. Okay. Great. So some of this I might leave as a little bit of an exercise, but we can go through part of it at least. Okay. So showing something is unique. Okay, if I want to show something's unique, how do I do that?
Assume they have 2 identity.
Yes. So assume there are 2 identities, and then what do I want to do? Someone else. 3.
By contradiction.
Yeah, by contradiction, so they have to be the same, basically. Very good, thank you. Very good. Okay, so let's suppose, so for part 1, it's good teamwork. So let's suppose we have 2 inverses. F and G are identities. Okay, well, what does it mean to be an identity? Just going back to that second axiom, it means when I multiply by any A, it gives me A back. Very good. So this means that F star A is equal to A. Oh, actually, and in fact, sorry, I should say this is the better way. So in fact, since F and G are both in G, right, it means that F star G should give me G back, right? And it means that G star F should give me F. Wait, is that how I want to do it? Do I want to do it this way? No, F star G should give me, there we go, sorry. I'll do it to F star G should also give me F back, right? Because either way I compose, the identity was 2-sided, right? This is equal to G because F was the identity. This is equal to F because G was also the identity. So what does that mean? This means, yeah, F is equal to G. Perfect. So if I have 2 identities, they're really the same thing. Okay, I can use a similar type of argument for inverses. Okay, so I'm going to put, for the interest of time, these are spelled out really nicely in the text, but 2 through 4 are exercises that are done really nicely in Dummit and Foote if you want to see them explicitly. But of course, uniqueness of inverses works similarly, right? So assume you have one element, you take A and you assume it has 2 different inverses, show that they're actually going to be equal, okay? And then part 4 is done sort of inductively. Okay, so one little thing, any questions about this proposition? Okay. So one thing I'll say that sometimes when we're talking about a group operation, instead of writing star or dot every time, we'll just kind of assume that the operation is multiplication when it's abstract, just for writing purposes. Okay, so we're gonna kind of, if it's a generic group, I might just write it as a multiplication operation. In that case, what that means is it just shortens my notation. So when I want to say like x star like a million times, right? I can instead just write x to the n, right? If I'm thinking of this. Okay. And similarly, if I'm multiplying inverses a bunch of times, I can just write that as x to the negative n. It's just a notation, a notational convenience that we're going to use. Specifically, of course, sometimes we're going to actually know that what the operation is, and if it's in that, like, say it will be addition. When it is addition, then I might write, of course, x plus x, even though, I mean, this is like, it feels like a dumb thing to write down, but this is like n times x. And same thing. Cool. Okay. So if you see n times x, usually it's just assumed, hey, that operation was addition. And then if you see, x to the n, it's like multiplication or abstract or something like that, just as a notational convenience. Okay. Last proposition, I think, that I wanted to cover was that we can solve equations using group operations. So let's say we have G as a group, and I have 2 elements in my group. The equations ax equals y, and ya equals, wait, is that one? Oh, sorry, ax equals b, and ya equals b, have unique solutions. Okay, so how do we solve something like ax equals b for x, so meaning I have unique solutions x and y. Well, how do I solve something for x? I would just multiply both sides by A inverse on the left, right? So, these aren't necessarily rational numbers or whatever, so I'm not going to divide, but what do I have? I have multiplication by A inverse. So I'm going to multiply A inverse on the left on both sides. And then, of course, I know that this is the identity. And so this is x A inverse B. And that is my solution. And the uniqueness just follows directly from the fact that we haven't proved it yet, but it's an exercise, that inverses are unique, right? A has a unique inverse, and so this thing is a unique solution, okay? Okay, great. Okay, so of course, that just solves one of the equations. You do the exact same thing for ya equals b. You just multiply on the right by A inverse, right? We have two-sided inverses every time, so we're good to go. Okay, great. So one thing that I should say is that we're out of time. So next time what we'll do is we'll talk about the order of the group, and we'll talk about dihedral groups in more detail and stuff like that. So cool. Let me know if you have any questions. Have a wonderful, yay, you survived the first day.